Advanced Financial Modeling, Topic 5, Fixed Income Portfolio Management, and Learning Objective Number 2. We're going to use duration to measure the sensitivity of a bond's price with respect to changes in the interest rates or discount rate or yield to maturity. So when we talk about the interest rate risk of the bond, what are we talking about? Well, in the last topic, we talked about the value of a bond is the present value of cash flows. So you can think of it as the sum of the present value of each cash flow. We talk about the interest rate risk of the bond. We're talking about as interest rates change, notably the discount rate or yield to maturity, how does that affect the value of the bond? Well, if this interest rate were to go up, the value of the bond would go down. So we say there's an inverse relationship between a bond's value and its discount rate or yield. The higher the discount rate, the lower the present value of cash flows. Also, we can infer that long-term bonds are more sensitive to changes in yield. Because you can think about a 10-year bond, a cash flow received 10 years from now. Well, that change in that present value effect is going to be taken to the 10th power. And if it's a 20-year bond, it's the 20th power. So that period magnifies the effect of the change in value. So we say longer-term bonds are more sensitive to changes in the discount rate or yield. So what we do is we need a measure of how sensitive a bond's price or value is with respect to changes in the discount rate or yield, and that measure is going to be called duration. All right, so duration is a measure of two things actually. It's the average cash flow timing. So it gives me a measure of kind of, is it a long-term bond or a shorter-term bond? And it also gives me exact measurement or approximation of the interest rate risk of the bond. And so it makes sense that we measure both things because I said that longer-term bonds are more sensitive. So duration is both a measure of how long the maturity is or the timing of the cash flows and also the interest rate sensitivity. What's confusing a bit about duration is there's several durations that we refer to. One is called Macaulay duration, which is going to be just a simple weighted average time to the cash flows. Then there's going to be modified duration, which does which is an adjustment to the Macaulay duration and tells me the actual price sensitivity. And then later we'll talk about effective duration. So let's talk about this Macaulay duration first. So the Macaulay duration is a measure of the average maturity of the bond's cash flows. It's simply a weighted average time to getting your cash flows in present value terms. So you can think of the Macaulay duration as a weighted average of the present value of the cash flows. So you can think about, when do I get my money? Well, I get my money at each period I. So if this were a one payment per year bond and it's a 5-year bond, you get your payments in, say, 1, 2, 3, 4, and 5. So what I'm going to do, this Macaulay duration is a weighted average of 1, 2, 3, 4, 5, and it's weighted by the present value of each payment divided by the total value of payments. The modified duration we'll show you in a minute is the Macaulay duration over 1 plus r to the f. So in some way you can think about it as the present value of the Macaulay duration. But it's easier to actually show you in a spreadsheet. So let's go to the spreadsheet. Let's go to bonds. And we'll go back to this example we had with this 5-year, 2 payment per year bond. And what we're going to do is we are going to calculate the weighted average time to getting the money. So it's kind of a weighting of the periods and the present value of cash flows. So I'm going to say equals the period divided by the frequency. So in this case, it's the first period is actually 0.5 years from now, 1 over 2. I'm going to anchor that frequency, and I'm going to multiply it times the present value of the cash flow divided by the present value of all cash flows. So I'm going to weight that 0.5 period by the fraction of the value that's received in period 0.5, or 1 year, 6 months from now. I'll copy that down. And what you see here is the sum is going to be the weighted average. You're weighting each period by the fraction of the value received in that period. So we say this bond, this 5-year, 2 payment per year bond, has a Macaulay duration of 4.07 years. Now, why does it make sense that it's 4 and not 5? Well, this bond makes payment, you get some fraction of its value in year 1, 2, 3, 4, and then most of the value is in year 5 when you get the final par payment. So on average, you get your money over 4 years, 4.07 years. So that's how you think of Macaulay duration. On average, in present value terms, you get your money over 4.07 years. Now, if this bond had a 0 coupon payment, so I'm going to make this coupon payment 0. Look what happens to the Macaulay duration. It simply goes to 5 because all your cash flows are received exactly 5 years from now. So what happens is the larger the coupon payment, the more the weighting gets weighted down below the maturity value. So there you go. There's my Macaulay duration. Now I'm going to calculate the modified duration. Modified duration is just going to be the Macaulay duration we just calculated divided by 1 plus R divided by frequency. And I have it there for you so you can see that the Macaulay duration divided by 1 plus the discount rate divided by the frequency is that modified duration. Okay, now you'll never have to do this in real life because I'm going to give you a function. That function is going to be called mod dur, modified duration. Now we've already played with this function here, bond val, and let's assume that bond val is in your Excel module, your VBA module. We're going to add the second program called mod dur, which is going to calculate the modified duration of the bond. So let me show you how this program works. Modified duration has 5 parameters. Actually, it's the same parameters as the bond val: coupon rate, par, T, frequency, and discount rate. And this is an interesting code in that it says V, the value of the bond, equals bond val. Now notice when you say bond val and I put open close brackets, it's actually referring to another function inside your module. So what this V is actually doing, it's actually calling on this function and execute this code to value the bond. So I'm using a function within a function, and notice the parameters that are exactly in the right order, the same order. So that allows me to value the bond without replicating the code of bond val. Now, why wouldn't I just replicate the code of bond val? Well, maybe you found a mistake in it, and then you have to correct it in 2 different places. So it's nice to have modular code, and that you can just create one piece of code, then refer to that code in another program. Okay, so I value the bond by calling on bond val, and then I figure out how many payments there are, T times frequency, and then I do the weighted average. For I equal 1 to n, next I, and it's mod dur equals mod dur plus, because I'm doing a weighted average of all the cash flows, and it is simply the present value of each cash flow times I divided by frequency. So it's doing exactly what we did in that spreadsheet, but it's doing it within this function. And then I have to handle the fact that this code here does not include the final par payment. So I need to add one more line of code to calculate the effect of the final par payment. And then if I ended the program right there, it would actually calculate Macaulay duration. The last step is take that value and divide it by 1 plus R divided by frequency. Then you have modified duration. Let's go back to the spreadsheet and let's go ahead and put in that function. So I'm going to delete that and I'm going to hit insert my function. User defined. I'm going to look for mod dur. I'm going to put in my coupon, my par, my maturity, my frequency, my discount rate, and there you see you get exactly 3.89 years as the modified duration. All right, so that's the mod-dir function. So let's talk about and use modified duration a little bit. So modified duration is the Macaulay duration divided by 1 plus r to the frequency. So it's in some sense the present value of the Macaulay duration, where Macaulay duration is the weighted average time to getting your money back. However, it could be shown that this modified duration is also the slope of the price-yield relationship of a bond. So if you were to graph the value of a bond and the yield to maturity or discount rate of a bond, and graph that function, and then at any particular price and yield, you could get a slope. So if this is the current price and yield of the bond, say this is the current value, this is the current yield, you would want to know the slope or the sensitivity of the bond's value to changes in its yield to maturity. You can calculate its modified duration. So that is exactly what modified duration gives you. It's roughly the slope of the price-yield relationship, but it's a little bit different. The Macaulay duration is the slope, and if you think of the slope, change in y, change in v over change in y, rise over run. So you can think of the modified duration as minus the slope divided by the value of the bond. So it's kind of a percent change slope. Also notice that I put a negative sign in front of modified duration because the price-yield relationship between a bond and the bond's yield and price is a negative relationship, right? Not positive. So, but we always quote duration as a positive number, so it's minus the percent duration. All right, so if we have this percent duration or percent slope concept, we can then use modified duration two different ways. Say you know that the change in yield of a bond is 100 basis points, 0.01. You could say the change in the value of the bond is minus the duration times change in the yield times the initial value of the bond. Or you can say, well, what was the percent change of a bond given a change in yield, say a 1% increase in rates? It would just be the change in yield times minus the modified duration. So this is the concept here of using the slope, this percent slope, that gives the interpretation of what modified duration actually tells you. If the modified duration of a bond is 4.9, like that last one, what it tells you is on average, if rates are up plus or minus 100 basis points, 0.01, then the percent change in the bond is 4.89% is the change in the bond. And if rates are up 100 basis points, on average, the price will fall by the duration. And if the rates are down, it will go up. So I want to do one more exercise before we end this section. I want to use our duration function to calculate changes in the price of a particular bond and talk about that. So let's go back to our spreadsheet. And I want to go to this tab or worksheet called Actual. So here is a 30-year bond, 10% coupon, 9%, go back to that. 30-year bond, there's the T equals 30, has 2 payments per year. Notice I valued a bond using bond val. I can get rid of the @ sign. Sometimes Excel inserts that, 1103.19. And we'll just assume that it's also selling for exactly its present value, 1103. In other words, you can think of this discount rate is also equal to the yield maturity since the bond is selling at its bond val. Notice I've calculated the modified duration of this 30-year bond. It's 10.187. So we're going to use that to estimate what would happen to the bond if the yield changes from 9 to 10, 11, or 12, or 9 to 8, 7, or 6, or plus or minus 1, 2, or 3 percentage points. So how you can use the duration function or value to calculate the change in value of the bond is I'll take minus the modified duration, anchor the modified duration, times change in yield. If rates are down to the yield is 6%, that's a 3% reduction in yield, times the initial value of the bond. 1103, anchor that. So minus the duration times the change in yield, which is not anchored, times the initial bond value. So if rates are down 3%, it should gain 337, or about 30%. Remember, duration tells you percent change for a 100 basis point change. So if it's down 3%, you gain about 30%. If the yield's down 3%. I'll copy this. And what this shows you is if rates are plus or minus 1%, the value is plus or minus $100. So these are changes in yield, changes in value. What would the actual new price of the bond be? Well, it gained 337. If the initial value was 1103, anchor that, the new value of the bond would be 1400. I'll copy that down. So this uses this uses modified duration to estimate what would happen to the value of the bond if rates are plus or minus 1, 2, or 300 basis points. Now I want to do one other exercise before we move on to this section. I want to actually value the bond, taking the present value of cash flows using these new yield and maturities, these new discount rates. So let's go ahead and put the bond val in there. I'm going to put in bond val. I'm going to put in the coupon rate, anchor it. The par, 1,000, anchor it. The maturity, 30 years, anchor it. The frequency, 2 times per year, anchor it. And the discount rate, I'm not going to anchor it. I'm going to click on the 6% right here. Because I'm going to value the bond if the yield to maturity were 6, 7, 8, 9, 10, 11, or 12. Copy. All right, so what we can see is if you actually valued the bond, this is the true value of the bond. Duration is an estimate. The duration price we estimated before is an estimate based on the duration. So there's a bit of a pricing error or valuation error. So if I just take the difference, my valuation versus the actual valuation, you can see I'm off. I'm $113 too low using duration as an estimate of value versus the actual value. I'll copy that down. So what this is showing you is duration is an estimate. If you use duration to estimate the value of a bond, what we say is it is a linear estimate. The actual price-yield relationship is a little bit different, and there's a bit of an error. So if I graph these two lines, this orange line here, this is the actual value of the bond if rates are plus or minus 300 basis points. This is what I estimated using duration. So you can think of duration as a linear estimate, or using duration to estimate the value is a linear estimate of what happens to bond val. It does a pretty good job here, right? If you look at small changes in interest rates, duration does a pretty good job. But when there's a big change in rates, there's big errors. There's big differences between the actual value of the bond and the duration estimated value. So we call that the duration error. Now, where is that error coming from? It's coming from the fact that if you actually graph the precise value versus yield change of a bond, you actually graph the actual bond function, it is a convex function. In other words, it's curved away from the origin. Duration assumes a linear relationship, so it's a straight line. So the error comes from the fact that duration provides a linear estimate, but the actual price-yield relationship of this particular bond is a convex function, and it's sloped. So just if I exaggerated this, duration is assuming a linear relationship. The actual price-yield relationship is convex. So for big changes in rates, you have that error in estimation. So that's what this next slide talks about, is that, or what this actually talks about here is the actual price-yield relationship is a curved away from the origin, which is convex, and we get these pricing errors. But don't worry, we can correct those pricing errors with something called convection convexity, which is our next section.